In the vast reaches of space, a star explodes with a brilliance that outshines entire galaxies, its core reaching temperatures so fierce they defy imagination. At the same moment, a comet hurtles silently through the cosmic void, its icy heart locked in a deep freeze colder than anything we've experienced on Earth. What connects these two extremes is one of the universe's most captivating secrets: temperature. From scorching infernos to bone-chilling voids, the universe is a place of wild contrasts where heat and cold shape the very fabric of existence. Today, we're diving into 30 astonishing facts about the universe's most extreme temperatures, uncovering mysteries that range from the fiery birth of stars to the coldest corners of space. By the end of this journey, you'll see just how these extremes influence everything from the tiniest particles to the grandest galaxies. Stick around because you won't believe what we're about to discover together. Now, let's turn our attention to one of the most mind-blowing extremes in the universe, the hottest known star. Meet WR102, a stellar powerhouse that burns so fiercely it makes our own sun look like a flickering candle. This star, located in the constellation Cygnus, which you might recognize as the Swan soaring through the night sky, reaches surface temperatures exceeding 200,000 Kelvin. To put that into perspective, our Sun, which is already incredibly hot, sits at a mere 5,500 Kelvin on its surface. That's right, WR102 is so hot that it glows an intense blue, a telltale sign of its extraordinary thermal energy. The blue hue of a star often marks it as one of the hottest in existence, and WR102 takes this to an extreme that's hard to wrap your mind around. But what makes WR102 truly fascinating is not just its heat. It's the fact that this star is in the final stages of its life, shedding mass at an alarming rate as it prepares for a spectacular end. And as we uncover more about stars like WR102, we begin to understand just how vital these blazing giants are in shaping the universe around us. With that foundation in mind, let's explore another extreme, this time something at the opposite end of the temperature spectrum. As we leave behind the fiery glow of WR102, let's take a cosmic detour to the farthest reaches of cold absolute zero. This is the universe's ultimate chill, a temperature so low that it seems almost impossible to grasp. At negative 273.15 degrees Celsius, absolute zero represents the point where atoms themselves slow to a near standstill. Now, you won't find this temperature in your everyday stroll through the cosmos, but there are places where the universe gets eerily close. One of those places is the Boomerang Nebula, a ghostly cloud of gas and dust located about 5,000 light-years away in the constellation Centaurus. What makes this nebula so special is that it holds the record for the coldest naturally occurring temperature ever measured outside a lab, just 1 degree above absolute zero. To put that in perspective, even the vast empty voids of space are warmer than this. So how does the Boomerang Nebula get so cold? It's all thanks to its dying star, which is expelling gas at incredible speeds. As this gas expands into the surrounding void, it cools down dramatically, creating a cosmic refrigerator unlike anything else we've discovered. The Boomerang Nebula reminds us that the universe isn't just a place of blazing stars and fiery explosions. It's also home to some of the coldest, quietest corners imaginable. And as we continue our journey through the extremes of temperature, keep in mind how these icy wonders help us piece together the mysteries of the cosmos. Speaking of extremes, let's now shift our focus to the heart of our own solar system, where temperatures soar to unimaginable heights. Now that we've ventured through the icy expanse of the Boomerang Nebula, it's time to turn our gaze toward the scorching heart of the cosmos, our very own Sun. Deep within its blazing center lies the Sun's core, an inferno where temperatures reach a mind-boggling 15 million Kelvin. To truly grasp the scale of this heat, Imagine a fire so intense it could melt through anything we know on Earth countless times over. But what's even more fascinating is the process happening inside this fiery furnace: nuclear fusion. This is the reaction that powers the Sun, fusing hydrogen atoms together to form helium and releasing an unimaginable amount of energy in the process. Without this constant, violent churning of particles, life as we know it wouldn't exist. Interestingly, despite the unimaginable fury in its core, the surface of the Sun is comparatively mild, with temperatures sitting around 5,500 Kelvin. That might still sound hot, and it absolutely is, but when you compare it to what's happening deep inside, it's almost like the difference between a bonfire and an erupting volcano. This contrast between the Sun's core and its surface highlights the incredible complexity of stars and their ability to sustain such extreme conditions. And as we explore these fiery processes, we begin to see how even something as familiar as sunlight is born from some of the most extreme temperatures in the universe. But the Sun isn't the only place where heat plays a starring role. Our next stop reveals another world where temperatures swing wildly between extremes, painting a picture of just how dynamic the universe truly is. Shifting our focus from the Sun's fiery depths, let's zoom in on a planet that experiences some of the most dramatic temperature shifts in the solar system: Mercury. This tiny, rocky world holds a big secret. During the day, temperatures on Mercury can soar to a blistering 427 degrees Celsius, hot enough to melt lead. But once the Sun dips below the horizon, the Mercury plummets to a bone-chilling negative 173 degrees Celsius. That's a swing of almost 600 degrees, and it all happens in the blink of an astronomical eye. So, what's behind this wild roller coaster of heat and cold? The answer lies in Mercury's lack of a substantial atmosphere. Unlike Earth, which has a protective blanket of air that traps and distributes heat, Mercury's thin exosphere does almost nothing to moderate its surface temperature. As a result, the side facing the Sun bakes under intense solar radiation, while the shadowed side radiates its heat away into the cold void of space. This stark contrast makes Mercury a perfect example of how the absence of an atmosphere can create some of the most extreme environments in the universe. It's a reminder that even in our cosmic neighborhood, conditions can vary wildly, shaping each world into something truly unique. And speaking of unique environments, our next destination takes us to a planet that might seem even more extreme: Venus, where heat and pressure combine to create a truly hellish landscape. Now let's turn our attention to Venus, a planet that might seem calm and beautiful from afar, but is anything but serene up close. Despite being further from the Sun than Mercury, Venus holds the title for the hottest surface temperature in our solar system, reaching a scorching 465 degrees Celsius. That's hot enough to melt lead and makes the planet utterly uninhabitable. But what makes Venus so brutally hot? The answer lies in its thick atmosphere, which is made almost entirely of carbon dioxide. This dense blanket of gas traps heat through an intense process known as the runaway greenhouse effect. Imagine wrapping yourself in a heavy, heat-absorbing blanket that never lets any warmth escape. This is essentially what happens on Venus. Sunlight penetrates the atmosphere, heating the surface, but the thick layer of carbon dioxide traps the heat, preventing it from radiating back into space. Over billions of years, this feedback loop caused temperatures to skyrocket, turning Venus into a nightmarish inferno. Interestingly, Venus's atmosphere also creates crushing pressures over 90 times stronger than Earth's, making it an extreme example of how atmospheric conditions can transform a planet into something completely hostile. As we pull away from Venus, it raises an intriguing question. Could other worlds in our universe exhibit similar runaway effects, or is Venus a one-of-a-kind cautionary tale? Next, we'll explore a much cooler destination, Europa, one of Jupiter's icy moons where water might exist in surprising forms beneath its frozen surface. As we journey away from the searing heat of Venus, let's shift our focus to a world that couldn't be more different: Europa, an icy moon orbiting Jupiter. Beneath its frozen, cracked surface lies a secret that has intrigued scientists for decades: a vast subsurface ocean. This hidden ocean is kept warm not by the sun, but by a fascinating process called tidal heating. As Europa orbits Jupiter, the massive planet's gravitational pull stretches and squeezes the moon, generating heat deep within its core. This heat prevents the ocean from freezing completely, even though the surface temperature on Europa can plummet to a bone-chilling -160 degrees Celsius. Scientists believe that in this dark, icy world, temperatures near the moon's rocky core could be warm enough to sustain liquid water, a crucial ingredient for life as we know it. The idea of a potentially habitable environment so far from the sun sparks endless curiosity about what else might be hiding beneath Europa's shell. What else could be lurking in the depths of this alien ocean, and could it hold clues to the mysteries of life beyond Earth? Next, we'll explore another moon, this time with weather patterns unlike anything we've seen before. Moving from the icy mysteries of Europa, we now turn our gaze to another fascinating world: Titan, Saturn's largest moon. Unlike any place in our solar system, Titan experiences weather patterns that are eerily familiar yet utterly alien. Picture this: rain falling from the sky, rivers carving through landscapes, and clouds drifting lazily overhead. But here's the twist: this isn't water we're talking about. On Titan, it rains methane, a substance that exists as a gas on Earth but becomes liquid in Titan's frigid environment. With temperatures plunging to around -179 degrees Celsius, the surface is a frozen wonderland where water ice acts like rock and methane plays the role of water. These methane rains feed vast lakes and seas, creating a cycle much like Earth's water cycle, but with chemicals that would freeze solid on our planet. It's a stark reminder of how diverse and adaptable nature can be, even in the most extreme conditions. What secrets might this icy, methane-soaked world hold, and how does it challenge our understanding of habitability? As we ponder these questions, we'll soon venture to an even more volatile destination, where fire and fury shape an entirely different kind of landscape. As we leave behind the icy methane rains of Titan, let's shift our focus to a place that couldn't be more different: a world where fire reigns supreme. Welcome to Io, one of Jupiter's moons and the most volcanically active body in the solar system. Imagine vast lakes of bubbling lava and towering geysers spewing sulfur into the sky. This is no ordinary destination. It's a cauldron of activity fueled by the immense gravitational pull from Jupiter and its other moons. Temperatures here can soar to an astonishing 1200 degrees Celsius, hot enough to melt most metals. These extreme conditions are driven by tidal forces that stretch and squeeze Io's interior, generating immense heat and powering its relentless volcanic activity. Lava lakes like Loki Patera dominate the landscape, glowing brightly against the moon's otherwise barren surface. Meanwhile, sulfur geysers erupt with such force that their plumes can reach hundreds of kilometers into space, painting Io's surface in vibrant yellows, reds, and oranges. It's a reminder that even in the cold vastness of space, nature can create environments of unimaginable heat and energy. But what does this volcanic fury tell us about the forces shaping other worlds? And could such extremes ever teach us something about Earth's own fiery past? From here, we'll journey to an even more distant and frosty world, where temperatures drop to levels that seem almost impossible to comprehend. Now let's drift away from the fiery chaos of Io and venture to a place that feels like the farthest edge of winter's grasp: Pluto. Here lies one of the solar system's most captivating features, the heart-shaped region known as Sputnik Planitia. Stretching across this dwarf planet's surface, it's a breathtaking expanse of frozen plains, smooth as glass and gleaming faintly in the dim sunlight. But don't let its serene appearance fool you. This is a land locked in a deep freeze where temperatures plummet to an unimaginable -229 degrees Celsius. At such extremes, even nitrogen gas condenses into solid ice, forming vast glaciers that creep slowly across the terrain. The stark beauty of Sputnik Planitia is unlike anything else in the solar system, a reminder of just how alien and diverse planetary environments can be. What makes this region truly fascinating, though, is how it came to exist. Scientists believe it formed billions of years ago when a massive impact carved out a basin, which later filled with nitrogen ice. Over time, the ice itself may have reshaped the entire planet, shifting its axis and giving Pluto its current orientation. It's a chilling yet awe-inspiring example of how even the coldest corners of the universe are shaped by dynamic forces, and it raises intriguing questions about the role of ice in shaping not just Pluto, but potentially other distant worlds as well. From this frozen heart, we'll soon explore an even stranger corner of the cosmos, where the temperature dips perilously close to the ultimate limit of cold. As we journey further into the chilling extremes of the universe, we arrive at a place that defies even the coldest temperatures we've encountered so far. Meet the Boomerang Nebula, a cosmic oddity that holds the title for the coldest known object in the universe, with temperatures dipping to just 1 Kelvin. To put that in perspective, this is just a hair above absolute zero, the point where molecular motion practically comes to a standstill. So how does this frozen marvel achieve such an extraordinary feat? The secret lies in its stellar winds. At the heart of the nebula is a dying star in its final stages, ejecting gas at incredible speeds. As these winds race outward, they expand rapidly, causing the surrounding material to cool down dramatically. It's similar to how a can of spray paint gets cold when you release its contents quickly, just on a cosmic scale. The Boomerang Nebula acts like a natural refrigerator, showing us how thermodynamics operates under the unique conditions of space. This icy expanse isn't just a record holder, it's also a natural laboratory, offering scientists clues about how matter behaves when pushed to the edge of what's physically possible. From this frosty corner of the cosmos, we'll turn our gaze to a world where the heat is far more intense, exploring an exoplanet that rivals the temperatures of some stars. Now let's shift our focus from the icy grip of the Boomerang Nebula to a world where the heat is so intense, it redefines what we think of as scorching. Imagine a planet where temperatures soar to over 4,300 degrees Celsius during the day, hotter than many stars in the universe. This is Kelt 9b, an exoplanet that orbits a blue giant star so fiercely that its surface feels more like the outer layers of a star than a planet. What makes Kelt 9b truly mind-blowing is not just its temperature but also the bizarre makeup of its atmosphere. Scientists believe that under such extreme heat, metals like iron and titanium don't just exist as solids or liquids. They actually vaporize, creating an atmosphere laced with metallic gases. To understand this, picture a world where molten metal isn't confined to science fiction, but is part of everyday reality. The heat here is so intense that it tears apart molecules, leaving the air filled with elements in states we rarely encounter. Kelt 9b serves as a stark reminder of just how varied and extreme planetary environments can be. It challenges our understanding of what planets are capable of enduring while offering a glimpse into the raw power of nearby stars. From this inferno of vaporized metals, we'll now explore another extreme in the universe where even the remnants of dead stars can surprise us with their peculiar traits. Moving from the searing heat of Kelt 9b, let's now journey to something far colder but equally fascinating: a faint glow that fills the entire universe. This is the cosmic microwave background radiation, often called the universe's oldest light. Imagine a moment just 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form, allowing light to travel freely for the first time. That ancient light is still with us today, stretched by the expansion of the universe into microwave wavelengths. At just 2.7 Kelvin, this glow is barely above absolute zero, making it one of the coldest things we can detect across the cosmos. What makes the cosmic microwave background truly remarkable are the tiny fluctuations within it. These subtle temperature variations, measured to incredibly precise levels, act like a cosmic fingerprint. They reveal the seeds of all the structures we see today: galaxies, stars, and even planets. Picture these fluctuations as ripples in an otherwise smooth pond, each ripple hinting at how matter was distributed in the universe's earliest moments. By studying this map of temperature differences, scientists have uncovered critical clues about the universe's composition, including the presence of dark matter and dark energy. It's like peering into a baby photo of the universe and seeing the blueprint for everything that followed. As we pull back from this ancient glow, get ready to explore another peculiar object in space, one that blurs the line between stars and planets. Shifting our gaze from the ancient glow of the cosmic microwave background, let's zoom in on a celestial oddity that challenges our traditional view of stars. Meet WISE 0855-0714, a brown dwarf that defies expectations. Unlike the fiery brilliance of most stars, this faint object is so cold it barely emits any light, with temperatures ranging from -48 degrees Celsius to a relatively balmy -13 degrees Celsius. To put that in perspective, this makes it closer in warmth to Earth's chilly winter days than to the scorching heat of a typical star. Brown dwarfs like WISE 0855-0714 occupy a strange middle ground between stars and planets. They form like stars but lack the mass needed to sustain nuclear fusion, leaving them dim and cool. What makes this particular brown dwarf stand out is just how close its temperatures are to those we experience here on Earth. Imagine a star so cold that it wouldn't even feel hot if you could somehow stand next to it. Scientists have been captivated by WISE 0855-0714 because it offers a glimpse into the boundary between what we classify as a star and what we might call a failed star or even a superplanet. Its discovery has sparked debates about how we define celestial objects and how these chilly outliers fit into the grand tapestry of the universe. As we leave this frigid world behind, prepare to uncover a phenomenon that combines beauty and chaos in equal measure, a storm so massive it has raged for centuries. Now, let's turn our attention to a spectacle of swirling chaos that has fascinated sky watchers for centuries. Jupiter's Great Red Spot is more than just a planetary beauty mark. It's a colossal storm that makes Earth's hurricanes look like gentle breezes. This massive tempest, larger than our entire planet, churns with winds racing at unimaginable speeds, and within its depths, temperatures soar above 1300 degrees Celsius. But what truly sets it apart is its longevity. Unlike storms on Earth that come and go in days or weeks, the Great Red Spot has been raging for at least 300 years and possibly much longer. Scientists believe it's fueled by Jupiter's internal heat and the planet's rapid rotation, which creates powerful jet streams that trap the storm in place. Imagine a hurricane that refuses to die, its crimson clouds swirling endlessly in an eternal dance of destruction and energy. The Great Red Spot isn't just a marvel of the solar system, it's a reminder of how diverse and dynamic planetary atmospheres can be. As we marvel at this centuries-old storm, get ready to explore another extreme environment where freezing temperatures reveal a different kind of alien world. As we leave behind the swirling storms of Jupiter, let's shift our gaze to a completely different kind of extreme environment, one that showcases the chilling realities of altitude and isolation. Picture this, a towering giant rising from an already cold and barren landscape. Welcome to Olympus Mons, the tallest volcano not just on Mars but in the entire solar system. Standing at nearly 22 kilometers high, this behemoth is so massive that its base would stretch across the state of Arizona. But its sheer size isn't the only thing that makes it remarkable. On Mars, where the average temperature hovers around -60 degrees Celsius, Olympus Mons takes the chill to another level. As you climb higher, the mercury plummets even further, sometimes dropping below -125 degrees Celsius. That's colder than the coldest temperatures ever recorded on Earth. Why does this happen? Well, Mars has an incredibly thin atmosphere, which means there's little to trap heat, especially at higher elevations. The result is a frostbitten peak that feels more like the outer reaches of the solar system than the surface of a neighboring planet. It's a stark reminder of how altitude and atmospheric conditions can transform an already harsh environment into something even more extreme. And with that icy picture painted, let's prepare to uncover another bizarre phenomenon where even water behaves in ways that defy our everyday experiences. Now, let's float into a realm where the rules we take for granted on Earth no longer apply. Imagine being in the vast, airless expanse of space, where even the simplest substances behave in wildly unexpected ways. Take water, for instance. Here on our planet, water boils at 100 degrees Celsius, a temperature we've all encountered when heating a pot on the stove. But in the vacuum of space, water doesn't need that kind of heat to transform into gas. In fact, it boils instantly at body temperature, around 37 degrees Celsius. Why does this happen? Well, without air pressure to keep the molecules in check, water shifts from liquid to vapor almost immediately. This phenomenon is a direct result of the lack of atmospheric pressure in space, where there's simply nothing to hold the liquid together. For astronauts, this quirk of physics has serious implications. If exposed to the vacuum, the water in their bodies would begin to vaporize, which is why spacesuits are meticulously engineered to provide a stable, pressurized environment. It's also a crucial consideration in spacecraft design, ensuring that all systems involving liquids, from life support to cooling mechanisms, function reliably in such extreme conditions. This strange behavior of water in space is yet another reminder of how different the universe can be from the world we know, and it highlights the ingenuity required to keep humans safe as we venture beyond our home planet. Speaking of extreme environments, let's now turn our attention to a place where stellar destruction creates some of the most mind-blowing temperatures imaginable. Now let's shift our gaze to a cosmic spectacle that truly lives up to its nickname. The fireworks galaxy, officially known as NGC 6946, is a dazzling display of celestial energy located about 22 million light-years away. This galaxy has earned its festive moniker because of its unusually high rate of supernova stellar explosions that light up the cosmos with incredible intensity. Since 1912, astronomers have observed 10 supernovae in this region, a frequency unmatched by most other galaxies. These explosions are not just visually stunning, they're also scorching hot, generating temperatures that soar into the millions of degrees. What makes these events so fascinating is how they reveal the life cycles of stars. When massive stars exhaust their fuel, they collapse under their own gravity before rebounding in a fiery explosion. This process scatters heavy elements like iron, carbon, and oxygen across space, which eventually contribute to the formation of new stars, planets, and even life itself. By studying the fireworks galaxy, scientists gain valuable insights into the birth, death, and rebirth of celestial bodies, painting a vivid picture of the universe's endless cycle of creation and destruction. As we marvel at this galactic wonder, it's hard not to feel a sense of awe at the sheer power and beauty hidden within the night sky. But the universe has even more surprises in store, so let's keep exploring these cosmic extremes. With the explosive brilliance of the fireworks galaxy still fresh in our minds, let's bring our focus a little closer to home and explore a quieter yet equally fascinating feature of our own solar system. This is the frost line, a boundary that plays a pivotal role in shaping the cosmic neighborhood we call home. The frost line marks the distance from the sun where temperatures drop low enough for volatile compounds like water, ammonia, and methane to freeze into solid ice. In our solar system, this boundary lies roughly between the orbits of Mars and Jupiter. Beyond this point, these frozen materials could accumulate and stick together, forming the building blocks of planets, moons, and even comets. This is why the inner planets Mercury, Venus, Earth, and Mars are small and rocky, while the outer planets Jupiter, Saturn, Uranus, and Neptune are much larger and made mostly of gases and ices. The frost line's influence doesn't stop there. It also explains why the asteroid belt located near this boundary contains a mix of rocky and icy objects, offering clues about the early solar system's dynamics. By understanding the frost line, we gain insight into why our solar system looks the way it does and how similar boundaries might shape planetary systems around other stars. Speaking of those distant stars, our next discovery will take us even deeper into the mysteries of the universe's most extreme environments. As we journey deeper into the cosmos, the story of creation unfolds in some of the universe's most breathtaking regions, stellar nurseries. These are places where stars are born, and one of the most famous examples is the Orion Nebula, a dazzling cloud of gas and dust located about 1,500 light-years away. Within these stellar nurseries, gravity pulls vast clouds of hydrogen gas together, causing them to collapse under their own weight. As the clouds contract, they heat up, with temperatures soaring to millions of degrees at their cores. This intense heat triggers nuclear fusion, the process where hydrogen atoms fuse to form helium, releasing an extraordinary amount of energy and igniting the birth of a new star. These fledgling stars often emerge surrounded by swirling disks of leftover material, which can eventually coalesce to form planets and other celestial bodies. The Orion Nebula, visible even with the naked eye under the right conditions, offers a glimpse into this cosmic cycle of birth and renewal, reminding us that the universe is not static but ever evolving. Understanding these stellar nurseries not only deepens our knowledge of how stars form, but also sheds light on the potential for life in other corners of the cosmos. Now, let's shift our focus to an equally awe-inspiring but much more explosive phenomenon, the death of stars. As we turn our gaze from the birth of stars to their dramatic endings, we find ourselves face to face with one of the universe's most explosive events, a supernova. These cosmic fireworks occur when massive stars exhaust their nuclear fuel and can no longer sustain the delicate balance between gravity and energy output. With nothing left to counteract the inward pull of gravity, the star's core collapses under its immense weight, triggering a catastrophic explosion that can outshine entire galaxies for a brief moment in time. During this event, temperatures skyrocket to billions of degrees, creating conditions so extreme that new elements are forged in the process. From oxygen to iron, and even heavier elements like gold and uranium, these stellar detonations scatter vital building blocks across space. These elements, in turn, become part of the cosmic recipe for forming planets, moons, and even life itself. In fact, much of what makes up our own planet, including the carbon in our bodies and the iron in our blood, was born in the fiery heart of a dying star. So, in a very real sense, we owe our existence to these spectacular celestial farewells, which remind us that destruction and creation are two sides of the same cosmic coin. Now, let's bring our attention back to one of the most hellish places in our solar system, where heat and pressure reach levels so extreme that they seem almost otherworldly, a place much closer to home than you might think. Shifting our focus now to a planet that often feels more like a vision of an alien nightmare than a neighbor in our own solar system, let's delve into the infernal world of Venus. This planet, often called Earth's sister due to its similar size and composition, is anything but hospitable. Venus holds the title of the hottest planet in our solar system, even though it's not the closest to the Sun. Its surface temperature soars to a blistering 465 degrees Celsius, hot enough to melt metals like lead. But why is this the case? The secret lies in its thick, oppressive atmosphere, composed almost entirely of carbon dioxide. This dense shroud traps heat in a runaway greenhouse effect, creating a pressure so intense that it's equivalent to being nearly 1 kilometer underwater on Earth. Combine this with clouds of sulfuric acid that reflect sunlight and trap thermal energy, and you've got a recipe for a truly hellish environment. Imagine standing on a surface where the air itself feels like a heavy, scorching blanket, and every breath, if you could somehow survive, would feel like inhaling fire. It's no wonder that Venus serves as a stark reminder of how delicate the balance of atmospheres can be. Now, with this vision of scorching heat fresh in mind, let's shift gears and explore the icy realms of the outer solar system, where temperatures plummet to levels that seem almost unimaginable in contrast. As we leave behind the searing heat of Venus and journey outward into the far reaches of our solar system, we find ourselves in a realm where cold dominates the landscape. Here, among the distant giants, Uranus and Neptune reign supreme as the ice giants, worlds cloaked in deep, frigid atmospheres that make them some of the coldest places in our cosmic neighborhood. While both planets share similarities, they also have distinct characteristics that set them apart. Uranus, for instance, holds the chilling title of the coldest planet, with temperatures plummeting to -224 degrees Celsius. These extreme conditions are driven by their unique compositions, as both planets are rich in methane, which gives them their striking blue hues while also contributing to their bone-chilling climates. Methane clouds swirl high above their surfaces, trapping what little heat they receive from the distant sun, but even this is not enough to warm their icy exteriors. Neptune, though slightly warmer than Uranus, still reaches frigid temperatures that challenge our understanding of planetary environments. These distant worlds remind us just how varied and extreme the conditions in our solar system can be, offering a stark contrast to the infernos we've explored closer to the Sun. Now, let's take this exploration of cold to an even more intriguing level by examining how these icy giants compare to some of the coldest objects found beyond our solar system. Shifting our focus from the icy giants to the cutting-edge technology that allows us to explore such extreme environments, we arrive at one of humanity's most impressive innovations, heat shields. These marvels of engineering are crucial for any spacecraft braving the inferno of re-entry or proximity to scorching celestial bodies. Take, for instance, NASA's Parker Solar Probe, a mission designed to study the Sun's outer atmosphere, or corona, where temperatures soar to millions of degrees. To withstand such conditions, the probe is equipped with a revolutionary heat shield made of a carbon composite material, capable of enduring temperatures up to 1,300 degrees Celsius while keeping the spacecraft's instruments at a comfortable operating temperature. This shield not only reflects most of the Sun's intense energy, but also ensures that the delicate electronics on board remain protected. Beyond the Parker Solar Probe, heat shields are a cornerstone of space exploration, enabling missions like the Mars rovers to land safely by withstanding the fiery plunge through planetary atmospheres. These advancements remind us of the ingenuity required to explore the universe's most extreme environments, bridging the gap between human curiosity and the harsh realities of space. With this in mind, let's venture even further into the icy outskirts of our solar system, where temperatures drop to levels that seem almost unimaginable. Venturing beyond the familiar boundaries of our solar system, we find ourselves in one of the most mysterious and frigid corners of the universe, the Oort cloud. This distant, icy expanse sits at the very edge of our solar neighborhood, stretching far beyond the orbit of Pluto. Temperatures here plummet to levels that are almost inconceivable, hovering just a few degrees above absolute zero. To put that into perspective, imagine a place so cold that even the tiniest traces of heat are practically non-existent. It's here, in this frozen realm, that ancient remnants from the solar system's formation have been preserved for billions of years, untouched by the warming influence of the Sun. These icy objects, composed of rock, dust, and frozen gases, offer scientists a unique glimpse into the conditions that existed when our solar system was still in its infancy. But the Oort cloud isn't just a cosmic freezer. It's also the birthplace of many comets that occasionally make their way into the inner solar system. These comets, triggered by gravitational nudges from nearby stars, begin their long journeys toward the Sun, creating spectacular displays in our night skies. However, the origins of these icy travelers are still a topic of lively debate among astronomers. Some believe the Oort cloud formed closer to the Sun before being flung outward during the solar system's chaotic early years, while others propose it was shaped by the gravitational influence of passing stars. Regardless of its origins, the Oort cloud serves as a reminder of just how diverse and dynamic the universe's temperature extremes can be. With this icy frontier now illuminated, let's turn our attention to something far more intense: the hottest known material ever created, a substance that simulates the universe's earliest moments. Stepping from the icy vastness of the Oort cloud into the realm of unimaginable heat, we encounter one of the most extraordinary materials ever produced: quark-gluon plasma. This substance, which exists only under the most extreme conditions, gives us a glimpse into the universe's infancy, recreating the environment that existed just microseconds after the Big Bang. Scientists have managed to create quark-gluon plasma in powerful particle accelerators, smashing heavy ions together at nearly the speed of light. In these collisions, temperatures soar to levels that are simply mind-blowing, reaching trillions of degrees Celsius. To put that in perspective, that's hundreds of thousands of times hotter than the core of the Sun. What makes this material so unique is that under these conditions, the building blocks of matter, protons and neutrons, break apart into their most fundamental components, quarks and gluons, which then flow freely in a state often described as a perfect liquid. This strange state of matter only lasts for a fraction of a second before cooling and recombining into ordinary particles, but its study has profound implications. Researchers believe that understanding quark-gluon plasma could unlock secrets about the early universe's evolution, shedding light on how the first particles came together to form stars, galaxies, and everything we see today. While it may seem worlds apart from the icy realms we just explored, this plasma reminds us how extremes of temperature, whether hot or cold, continue to shape our understanding of the cosmos. With this fiery revelation behind us, let's now shift our focus to a completely different kind of extreme, an environment so cold it pushes the boundaries of what we think is possible in nature. As we leave behind the searing heat of quark-gluon plasma, our journey through the extremes of temperature takes a sharp turn toward the other end of the spectrum. This time, we're diving into a realm so frigid it challenges the very limits of what we consider possible. At the Massachusetts Institute of Technology, researchers have achieved something truly extraordinary in their labs: temperatures that hover just billionths of a degree above absolute zero. That's right, colder than the coldest corners of space itself. These groundbreaking experiments have opened up entirely new ways to study matter, particularly in the weird and wonderful world of quantum physics. At such unimaginably low temperatures, atoms behave in ways that seem almost magical. Instead of bouncing around like they normally would, they slow down to the point where quantum effects dominate, forming strange states of matter like Bose-Einstein condensates. In these conditions, particles start acting as if they're part of a single, unified entity, losing their individual identities. Scientists believe that studying these ultra-cold environments can teach us a lot about the fundamental rules governing the universe, with some surprising connections to the stars and galaxies far beyond Earth. For instance, the way atoms interact in these super-chilled states mirrors some of the behaviors we observe in neutron stars or the early universe, bridging the gap between the tiniest particles and the vastness of space. But achieving such extreme cold isn't just about breaking records, it's about pushing the boundaries of what we know and paving the way for future discoveries. With this icy milestone now behind us, let's turn our attention to the grand finale of our cosmic temperature journey, the universe's own timeline of heat and cold that has shaped everything we see today. With our exploration of extreme temperatures nearing its end, we now step back to take in the bigger picture, the universe's own temperature journey. From its explosive beginnings to the vast, cooling expanse we see today, the story of cosmic heat is one of dramatic transformation. It all started with the Big Bang, an unimaginably hot event where temperatures soared into the trillions of degrees. In those first moments, the universe was a chaotic sea of energy, far too hot for atoms or even particles as we know them to exist. As it expanded, though, the heat began to drop, allowing the first building blocks of matter to form. This cooling process didn't stop there. It shaped everything that followed, from the birth of stars to the spread of galaxies. Even today, we can still see the echoes of this early heat in the form of the cosmic microwave background, a faint glow that tells us the universe now rests at a chilly 2.7 Kelvin. Yet, this gradual cooling hasn't meant the end of activity. Instead, it's created a dynamic balance where extreme heat and bitter cold work together to shape stars, planets, and even life itself. It's a story that reminds us how the universe's temperature isn't just a number. It's a driving force behind the wonders we see scattered across the cosmos. And with that, our journey through 30 astonishing facts about the universe's most extreme temperatures comes to a close. If you've enjoyed this cosmic adventure, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update. What's your favorite fact from today's video? Let us know in the comments below. We'd love to hear from you. As we bring this cosmic journey to a close, it's worth marveling at the sheer diversity of temperatures that define our universe. From the blistering heat of newborn stars to the bone-chilling cold of distant nebulae, these extremes are more than just numbers. They're the forces that mold galaxies, ignite stellar furnaces, and even make life on Earth possible. Each fact we've explored adds a new layer to our understanding of how deeply temperature influences the cosmos. So take a moment to reflect on the wonders we've uncovered, from fiery supernova to the icy stillness of the Boomerang Nebula. If this voyage through the universe's hottest and coldest corners has sparked your curiosity, show your support by subscribing to the channel and hitting the notification bell. Drop a comment below to share which fact amazed you the most, and don't forget to share this video with fellow space enthusiasts. Together, let's keep exploring the mysteries of the universe one fact at a time.